morning.
Good morning, girls.
Good morning.
Good morning, Dan. Okay.
Good morning.
Good morning, Dan.
Good morning.
Okay. Sure. Okay, ladies. Let's see.
I have a question. before we
Yes,
start.
go ahead. Yes.
Do we have to know the focal depth, the formula for it? I was reading over the weekend, for chapter 9. Do we have to know the diameter times the frequency?
No.
Okay.
Let me see which one they're talking about.
And we don't have to know the divergence.
Send divergence saying no. That's too much. Okay, ladies. Any questions about axial resolution? Any questions about axial resolution? Nope. Okay. Oops. That's too much. Then we can go on to the next layer resolution, which is going to be your lateral resolution. Okay. And go before we go into the details of the lateral resolution, we can make this this is going to be determined by the beam. So just like for your axial resolution, if you didn't understood your pulse or your spatial pulse length, etc., it was a little bit of difficult to understand. So likewise, for this one here, it's okay. What you need to understand is the beam. Okay, what were the yes, okay, components of the beam? How was it that okay, as a beam actually is okay behaved? And we already have said that okay, yes. When the sound wave is okay, change something that goes like this, that will be called a beam. Now, first of all, is okay, how do we define lateral resolution? Clear. Okay, now we already also said the other day that okay, yes, this here, that was okay, yes, because it's okay, the main axis of the beam. Clear. Okay. So again, yes, okay, resolution that's going to be conveyed as okay, the ability to, I guess that's okay, distinguish between, yes, okay, structures. Okay. Now the word lateral is okay, that's a good term because that's okay, what does the word lateral mean? On the side, right? This means okay, going to be as okay, the ability to distinguish between structures that are side by side. Or what your book also is okay, say is perpendicular to the beam's main, okay, sorry, beam's main axis. Okay. Now, let us just see what that means. We said, for instance, okay, if we've had a beam. Here, okay, and at some point, it's okay, the beam is going to be at its narrowest, which we'll call the focus. In this, we could say, it's okay, if for instance, okay, this here is okay, that was the main axis of the beam. There. The other day, we talked of pulses because okay, what we mainly will have in the beam is going to be as okay. We can say as okay pulses. So we can mean as okay the ability to distinguish between it's okay this structure here, and for instance this structure here. That was what we call the axial resolution. Clear. Where we also can say as okay as we go from here, because this was your transducer, and that's the mean is okay just going to be an, we can say as okay increasing depth. Okay. Now what this mainly is okay, what they mainly is okay, name these structures here to be as okay, they were going to be parallel to the beam's main axis. Whereas where we say, and actually it's okay, our ability to is okay, distinguish these two structures here from one another, that mainly meant we had a good axial resolution. If we weren't able to distinguish these two structures from one another, that would have been a bad axial resolution. Yep. Now, for your lateral resolution, as they say, it's okay, is going to be, it's okay, the ability to distinguish between structures, okay, that are side by side. or perpendicular to the beam's main axis. Did that make sense?
Yes.
Okay. Okay. So that's okay for your axial resolution. That was dependent upon as okay, was the pulse small enough to yes, okay, distinguish between these two structures, or the pulse too big that okay, these two structures here would have appear as one shadow. Clear? Okay. Whereas okay, as far as okay, your lateral resolution is going to be determined, you will see that is going to just okay, mainly be dependent upon as okay, the shape, the nature, and so on, so of your beam. But what is it that the lateral resolution is going to be as okay, the ability to distinguish between two structures or structures that are side by side to one another. Okay. That says okay, if this was a beam, for instance, okay, this would have been, let's say, okay, on the right side of the beam. This would have been as okay, let's say, as okay, on the left side of the beam. And if your system was able to just okay, distinguish these two structures here as separate structures, that may mean that okay, you will have a good lateral resolution. Whereas if these two structures here, for instance, okay, were smushed together, let's say it's okay that they are located something like this, and again, yes, okay, in relation to the beam, that will mainly mean that okay, as stable, these two structures here will show up as one reflector, and that will be as okay, a bad lateral resolution. But they have to be side by side. Okay, so if you look at an image, for instance, clear, or ability to as okay, distinguish, let's say as okay, this structure here from this structure here. Okay, that is axial resolution. Clear, and that was mainly going to be as okay, the pulse or your spatial pulse length that will determine whether you had a good or bad axial resolution. All dependent upon as okay, the numerical value. How did we determine the numerical value of the axial resolution? Your spatial pulse length divided by 2. Okay, but this is how yes, okay, your pulses will go. Okay, and we can say okay, then reflect back. Then another pulse is okay, reflect back. Whereas okay, in all this, we can say okay. Now this here is okay, maybe your beam, for instance. Clear. Whereas okay, now if we are looking at okay, as which two structures is going to yes, okay, be distinguished to give us a good lateral resolution, it will be this. So they have to be as okay, side by side. Clear. Okay, and that's mainly as okay, where the word lateral comes into the, because what the word lateral actually means is okay, L is okay, pertaining to side. Yeah.
I have a quick question.
That's a check. That's a check. Let's see. Okay, there. Okay. So side by side. Now we can say it's okay. At a greater depth, for instance, okay, we may have two structures which are at the same distance. But down here, the distance between the two are the same. Okay, side by side. Let's say it's okay. Here the distance was, let's say, assume. For instance, okay, 1 centimeter apart. Even here, it's okay. The distance between these two structures here is 1 centimeter apart. But what we will have at this level here is that, okay, these two structures is, okay, that will give us a good lateral resolution. Whereas here, you will have a poor lateral resolution. Yes, Shaq, you had a question there?
So for the lateral resolution, it can be out of the beam or inside.
Okay, we're going to come to that in just a little bit, okay?
Oh, okay, okay.
Yeah, that's not much mama. Clear? Okay. But the whole thing, just like your lateral axial resolution, is okay, what we said, axial resolution, for instance, had, okay, so it had a numerical value. Clear? What was the numerical value for axial resolution? The spatial length divided by 2. Clear? Right? Okay. Now, what will determine whether you had, okay, as a good axial resolution, or whether you had a bad axial resolution or a poor axial resolution? That was mainly as okay because it's okay comparing the numerical value to as okay the distance between the two structures. Now, if your numerical value was lesser than the distance between the two structures, you will have a good resolution. In this case, it's okay, we are talking about is okay, structures being as okay, superficial and deep in relation to is okay to the numerical value of your axial resolution. Whereas, okay, if the numerical value of the distance, okay, of the resolution was lesser, was lesser than the distance between the two structures, then you will have a good resolution. Now, what the hell am I talking about? Sorry. Okay, sorry. If the numerical okay value was less, then you have okay, it's a good resolution. Sorry. Right, okay. You will have a good resolution, whereas the numerical value was greater, you will have a better resolution, or you will have a bad resolution or poor resolution. Yeah. So the same is going to apply to your lateral resolution. So the question just comes as, okay, what is the okay? What is okay as the numerical value of lateral resolution? Now, first of all, it's okay, before getting into it's okay, what the numerical value is. What we said was okay, as what was the unit in which lateral resolution is expressed. I already mentioned that the other day because it says, okay, lateral resolution was an example of spatial resolution, which was going to use a unit of space, which would be something like centimeters, millimeters, exactly, yes, okay, to indicate the numerical value of your lateral resolution. So that's going to be used, expressed using a unit of distance. Why? Mainly because lateral resolution was a type of spatial resolution, a resolution in terms of pertaining to space, area, distance, etc. Did that make sense?
Yes.
Good. The next thing would be as okay, what determines your lateral resolution? And ladies, that is going to be as okay, your source that determines the lateral resolution. Which part of the source? Well, okay, and again, it's okay. Now that's going to be okay, something we talk more about in chapter 14. Because that's something that's going to be known as a beamer, or what we call it, okay, a beam former. But it's okay, you look at it as okay, that means it's okay, going to be as okay, the component of the system that forms the beam. And your lateral resolution is, because it's okay, related, and hence determined by the beam. Right. Did that make sense? So it's going to be as okay, all dependent upon as okay, what your beam looks like. That will determine whether you have a good axial resolution or a bad axial resolution. No, lateral resolution, sorry. Okay. Now
Okay.
goes.
Can you repeat that one for me?
It's all going to be dependent upon, yes, okay, how your beam looks. Or we can, or like to say, yes, okay, the measurements of your beam that will determine whether you have a good axial lateral resolution or a bad lateral resolution. Okay. Now, if you look at what a beam looks like, yes, okay, it's not going to be the same at all depths. Right, okay. You said, okay, yes, if this here is okay, what's your beam? What do you see? At some point, is the beam is going to be wide. At some point, is it going to be, yes, okay, narrow. And we guess okay, at some point, it's going to be, yes, okay, at its narrowest. So you can actually say that, okay, yes, at, because okay, we go from here, which was okay, so it's okay, our source or transducer. We actually, it's okay, will have You go deeper and deeper and deeper and deeper and deeper. And at different depths, you're going to, yes, okay, end up having different lateral resolutions. Did that make sense?
Yes.
What's going to determine what your lateral resolution is going to be? It's made as okay, going to be determined as okay, how wide your beam is at a certain depth. Whether you get a good lateral resolution or a bad lateral resolution at those depths is going to again be as okay determined by as okay which of the two is greater, which of the two is lesser. Is it the distance of the structures that lie side by side? Or as we say, it's okay, perpendicular to the main axis of the beam that is greater than the width of the beam. If this distance here is greater than the width of the beam, yes, okay, you have a good lateral resolution. If the width of the beam is greater than the distance between two structures that lie perpendicular to the main axis of the beam or lie side by side, then okay, in this case, that's okay, you would have a bad lateral resolution.
I heard you. Can you explain it again? Because it's not like
We're
registering.
coming to it once we talk about the numerical values there. Okay?
Okay.
Yeah. Now the synonyms, ladies, of your lateral resolution. So your lateral resolution can also be known as angular resolution. It can also be known as transverse resolution. And or it can also be known as azimuthal resolution. So these are all, yes, okay, different terms that can be replaced or can replace the term lateral resolution in the text, in the question, in the discussion. Okay. Now, if you just look at an opposite here, for instance, that's okay, that's okay, transfer resolution for your axial resolution. That was something that we called longitudinal. Okay, so that's okay. We can mainly say it's okay that these two terms here, I mean, that's okay. Referring to, yes, okay, the relation between structures is okay to one another along, yes, okay, the beam's main axis. Because, okay, for your longitudinal resolution or axial resolution, the structures were along, it's okay, related to one another along the beam's main axis. And that's what we call longitudinal. Just like, okay, as we said, that sound wave was a longitudinal wave. What did that mean? As the sound travels in this direction, the particles move like this. We can then look at the transfers. If you recall, you said, okay, the wave was moving in this direction, and the particles were moving like this. That was a transverse wave. This is a kind of thing. So again, transfers. Transfers to what? A line transfer here, it's okay, to the beam's main axis. Did that make sense? Angular I made as okay, just because it's okay, you can say it's okay, it makes an angle. And some of you may ask me, Mike, so where did this term here, azimuthal, come from? Well, okay, let me be honest, I never heard of that before myself either. The first time I came across it was in this book. So that's okay. I Google searched it as well. And okay, as this is mainly as okay, something that they use in okay as astronomy. Studying of okay, as you can say, it's okay, the stars and planets and so on. So okay. Now I may know a lot of crazy things, but okay, as how to look at the stars and find formations and so on. So yes, okay, I have no idea about all that. So yes, okay, that's okay. That's where they imported that term from. Okay, but for you go, that's okay. Just remember that. Okay, as the other three names for your lateral resolution is angular, transverse, and okay, yes, azimuthal. Did that make any sense?
Yes.
Good. But if you look at it, it's okay, the term transverse and the term longitudinal for respectively lateral resolution and axial resolution is mainly as okay because it's okay relating the location of structures to the main axis of the beam. Which will determine as okay whether they were going to be able to distinguish it clearly or not clearly to give us okay as a good or bad, distinguish it clear or not distinguish it clear to give us okay as a good or bad resolution. Okay. Now, ladies, the numerical value of your lateral resolution. So numerical value of it says okay, lateral resolutions. Numerical value is made as okay, just going to be equal to the beam's width. Okay. Now just keep in mind here, girls, and that's going to be as okay important because width that is made as okay, that's going to as okay be because okay is determined by how wide a beam is. Clear? And when we say wide, what does that mean? Side to side dimension of the beam, right? that is going to be as okay the width. And goals. Now, for now at least, that's okay. Whenever we has okay, chalk of a beam. Okay, and we draw a beam. Just assume like, okay, as we are looking at a beam from above. Where we can then say, okay, that this here is okay. This will be as okay, let's say it's okay, the right side of the beam. And this one down here, for instance, okay, can be, it's okay, the left side of the beam. Is that clear? So for now, yes, okay, just at least whenever yes, okay, chalk lateral resolution. And we draw a beam to yes, okay, explain that. Just assume that, okay, that we are looking at the beam from above. Clear? Okay. Where we can mean, yes, okay, then say that this will be a right side, this will be a left side. And what is this going to be? This distance here. That's going to, yes, okay, we can say it's okay, the width of the beam. Likewise, this distance here, that's going to be, yes, okay, the width of the beam. This distance here, that's also going to be, yes, okay, the width of the beam. This distance here is also going to be, yes, okay, the width of the beam. And we can go on. We can say it's okay, all these distances here from side to side is going to, as okay, mainly determined, or be determined upon or by how wide is it that the beam is. And then it's okay, in the whole course of the beam, yes, okay, we come to a point where the beam has the smallest width, which mainly will mean that, okay, as it is narrowest. Did that make sense?
Yeah.
Which means, okay, the point where the beam has the narrowest width. Mainly will mean that, okay, yes, this is where, okay, yes, the lateral resolution has the lowest numerical value. Whereas that says, okay, at this point here of the beam, we can mean it says, okay, that's where, okay, yes, the lateral resolution has the greatest numerical value. Because what we mainly said the numerical value of your lateral resolution is the width of the beam. So here is okay, there is no division, there is no multiplication, there is no addition, there is no subtraction. Okay, because okay, at any point you say, yes, okay, well, this is the width of the beam. That width of the beam is going to be equal to, yes, okay, the numerical value of the lateral resolution. Clear? Because this width here, yes, okay, that's still going to, yes, okay, be expressed in a unit of distance. We can say it's okay, that may be millimeters, that may be centimeter, that may be micrometers, that may be whatever. And so it's okay, it's going to be, it's okay, the numerical value of your beam is also going to be expressed in unit of distance, millimeters, centimeters. Mainly because it's okay, this would be as okay, be the same as okay as the width of the beam. And that becomes just okay the numerical value of your lateral resolution. But mainly as we see that okay, yes, there are beam, what happens to it? Well, okay, yes, in the near zone. What happens to the beam in the near zone? Yes, ladies. What happens to the beam in the near zone?
It starts to narrow out. And
It starts to narrow, right? Okay, so it means it's okay going to converge, or we can mean it's okay become narrower. What does this narrowing mean? That okay, at the lateral resolutions, numerical value decreases in the near zone, right? Did that make sense?
yes,
Then we get to yes, okay, we can say yes, okay, the narrowest point, which we call as okay, the focus or the focal point, right? But had we had the focal point down when you can say okay that the beam was at its narrowest. Now, what does it mean to be the narrow down? It means that okay, as the lateral resolutions, numerical value is at its lowest. Did that make sense? So at the whole course of the beam, the point where you have the lowest, or okay, how the lateral resolution has the lowest numerical value is going to be the point where the beam is at its narrowest, or we can say okay, at its lowest width. Did that make sense? Well, okay. If
I have a question.
Yeah.
So the beginning of the near zone has the highest and the focus has the lowest numerical value.
Yeah.
Okay.
Because what did we say the numerical value of your lateral resolution was? Directly as okay, the width of the beam. At this point, you can say, okay, this distance here is okay, may measure, let's say, as okay, 6 millimeters. That will be as okay, the numerical value of your lateral resolution at this point here. Whereas, okay, as we said earlier, as okay, the focus as okay, the beam is going to have okay as a diameter, which was half of the beginning. So it's okay, here is okay, this distance here is going to be, oh shit, sorry. Because it's okay, this distance here, or the focus, the width of the beam is going to be as okay, 3 millimeters. Right? Where the width of the beam at any point is going to be as okay, the numerical value of the lateral resolution. So here it's okay, 6 millimeters. Because it's okay, this 6 millimeters is okay, that was a great width of the beam, which may mean that okay, you have a great numerical value of the lateral resolution. Did that make sense?
Yes.
Good. There here, you say, well, okay, the beam is narrower, or we can make it okay that the beam have a lesser width, right? Which means that okay, as this point is okay, the beam has a, or we can say okay, the lateral resolution's numerical value is going to be less. As a matter of fact, here it's okay, it was 6 millimeters. Whereas, okay, as at this depth here at the focus, it was going to be as okay, we can say it's okay, 3 millimeters. Did that make sense?
Yes.
Good. Next is, okay, what happens to your beam in the far zone? What happens to the beam in the far zone?
Starting to widen.
It widens or it becomes, it diverges, which mainly will mean that, okay, it will increase in, I'm going to say, okay, increase in width, right? Which mainly means that, okay, the farther and farther and farther we go into the far zone, we are okay an increasing numerical value of the lateral resolution. Did that make sense? Now goes, what did we say that the relationship between the numerical value and resolution was? We actually, as okay, said that the relator, okay, as the greater a numerical value, the poorer the resolution, or vice versa. The lesser the numerical value, the greater, or it's okay, better the resolution, right? Right?
Yes.
Okay. Now, what was you can say it's okay for your lateral resolution? What was the numerical value here? That was going to be, it's okay, the beam's width, which mainly mean that, okay, at some point, it's okay, where we have a greater numerical value of the beam, which mainly will mean that, okay, as the beam has a greater width, that will be as okay, where we will have a poor resolution. Or vice versa. The points where we have, okay, as a low numerical value of the lateral resolution, which will mean that the beam has a lesser width. That will mainly mean that we have a good lateral resolution. Where we can say, okay, most likely it's in the entire course of a beam, where we have, okay, have the best lateral resolution is going to be as okay, where the numerical value of the beam is at its lowest, which mainly will mean that, okay, the beam is going to be, or the width of the beam is going to be at its lowest. And where do you usually find that? At the focus. Now goes here as okay, this numerical value has still to be as okay compared to the distance, to let's say it's okay, the distance between structures that lie side by side. Or as we said in the definition, perpendicular to the main axis of the beam. Did that make sense? Now we can say that, okay, as we have a transducer. It produces a beam. Now, what do we see here? Now, since the beam of the width of the beam is greatest, all the yes, okay, the distance between yes, okay, the two structures here is the same compared to here, Well, it's okay, this is going to, it's okay, this great wider beam is going to call that, okay, as you have, okay, as a greater numerical value of the lateral resolution, which means we'll cause it to be poor. Where, okay, we can say that at some point, it's okay, the beam is okay, it gets to, it's okay, it's focus. Clear? Although it's okay, the distance between is okay, the two structures are at the same distance from one another. Because okay, this distance here was, let's say it's okay, 2 millimeters. We can say, so is this distance here also going to be 2 millimeters? We can even say it's okay that this distance here is also going to be 2 millimeters. Where okay, here yes, okay, this distance is greater than 2 millimeters. Or we can say that the width of the beam is greater than 2 millimeters. Let's say that okay, here it is 3 millimeters wide. At this point here, right? Okay. Yeah. So that will actually give you as okay a bad lateral resolution. Yes, okay, the distance between the two structures, which are side by side to one another, is still 2 millimeters. But we can say, okay, the beam is going to be as okay, the width of the beam at this point here is less than 2 millimeters. Let's just say 1.5 millimeters. Oh, okay. Where we can mean says, okay, at this point here, okay, the focus is okay, the numerical value that is going to yes, okay, be lesser than the distance between the two structures. But the point here is okay, that these two structures here have to be side by side. Or as we may also say, it's okay, perpendicular to the beam's main axis. But mainly because okay, this is okay, the numerical value is lesser than the distance between the two structures that are called okay as we here we have okay, it's a good, or we can say okay, the best axial resolution in the entire course of the beam. That's going to be the point where we will have the best axial resolution, not lateral resolution, sorry. Yeah. So we can still say it's okay now, okay. It may go like this. It may go like this. Well, okay, yes, we can say it's okay. The distance here was 2 millimeters. We can say it's okay. Even the beam, for instance, okay, at this point here was 2 millimeters. So that may not give us the best, but it's still going to be as okay. We can say that's okay, good. Why good? Because okay, the beam of the diameter, or the diameter of the beam, or the width of the beam is at least okay equal to the distance between, yes, okay, the two structures which are side by side or perpendicular to the beam's main axis. Okay. So just like in your axial resolution, what did we do? We compared the distance between the two structures, which one was in front or back or shallow or deep to one another. Compared to what? To half the spatial pulse length. Clear? Because that half spatial pulse length, that was your numerical value of the axial resolution. Did that make sense? Right. Okay. Now, if that numerical value is okay was lesser than the distance between the two structures, superficial deep, you had a good resolution. If that numerical value was greater, you will have a bad or poor axial resolution. Now the same as okay here applies to your lateral resolution. Now the lateral resolution, what did that have? I was going to yes, okay, determine that the width of the beam. Okay, and that's why I told you girls that's okay Friday, read on your beam. Okay, but what you should know at least is okay that as the beam travels, in the first part it keeps on narrowing down. Then it gets to its narrowest point, and then afterward, which you call the focus or focal point, and then it spreads out. So yes, okay, at different depth, what happens? The beam has different widths. Okay, where we can say is okay, in the beginning, yes, okay, the beam is at its widest. At its focus, it's at the narrowest. So that width of the beam at just okay, different points is going to just okay determine the lateral resolution of the beam at that depth. So what is it that your lateral resolution does? It changes. Clear? Okay. But where you can say is okay, in the near zone, it will be poor. In the far zone, it will be poor. The point where it's okay in the entire course of the beam where you will have the best lateral resolution is going to be at the focus. Because what happens at the focus, that's when the beam is at its narrowest, which means to me, yes, okay, it has the lowest numerical value for the lateral resolution. And the lower the numerical value for any resolution, the better is it that resolution will be. Did that make any sense?
Yes.
Right, okay. So that's why we said just okay, higher numerical value, poor resolution. Greater numerical value, no, sorry, lower numerical value, better resolution. Right, okay. So what was your numerical value here? width of the beam. Wider beam? Well, okay, that would mainly mean that, okay, here, there has to be, yes, okay, a greater distance between, yes, okay, structure to structure for it to, yes, okay, I'll give you a good lateral resolution. Where, look at the focus, or as the beam narrows, the width narrows down, so is going to be as okay the likelihood or the ability of this beam is okay to distinguish between two structures that are closer to one another. Okay, but please keep in mind, girls, for your lateral resolution, those structures have to be side by side. Side by side. Okay. Any questions? Now let us just put it this way. This here is okay, that's the width. This dimension, right? Okay. Now, if I was a beam, for instance, and that's okay, my shoulder span, well, let's say it's okay, 4 feet. Let's just assume. All that mean that for me to be able to pass just okay through a door without either shrugging my shoulders together or something, you have to make a door which is at least 4 feet wide, right? Did that make sense?
Yeah.
Okay, so that will mean it's okay, you can say it's okay, a good lateral resolution. You can make a door that is 6 feet wide or 8 feet wide or 12 feet wide. That width of the door is just going to be, it's okay, we can say it's okay, the distance between, it's okay, the two particles or structures side to side. Right. But if that door, that's okay, is wide enough for me to walk through without having, it's okay, to shrug my shoulders. That may mean that, okay, as we have a good lateral resolution. Because the width of the door frame is greater than the width of my shoulders. Did you guys get that?
Yes.
Do you guys want to hear a little joke about a bad lateral resolution?
Sure. Is it
Now, in the
bad?
dark night, yes, okay, a guy, he was riding on his motorbike down the street or highway or road or whatever you want to call it. Now, what he see ahead of him is 2 headlights. And what goes through his mind is, okay, those are 2 guys riding on a bike, side by side. So wouldn't it be fun if I run my bike right in the middle of them? But those headlights are okay, approaching him, and he is approaching those headlights. And he carries out his plan. The next thing he remembers is, well, okay, that's the last thing he remembers. When he wake up again, yes, okay, he is in a hospital bed. And I just awoke from, okay, and the doctor says, well, okay, well, you survived. And here's, okay, this is the truck driver whose truck you ran into. So he was trying to just, okay, have a good lateral resolution there. trying to, okay, pass in between those two lights. He didn't realize that, okay, yes, it was not two bikers riding side by side, but actually it's okay, a truck. But yes, so the thing is, if the beam's width is greater at any point than the distance between two structures which are side by side or perpendicular to the beam's main axis, then, okay, yes, that will be a poor lateral resolution. Whereas if the beam's width is less than the distance of two structures side by side or perpendicular to the beam's main axis, that will become a good lateral resolution. Clear? Now, contrary to your exit resolution, I say, yes, okay, your spatial pulse line, that is going to be the same at all depths. So what determined, yes, okay, your spatial pulse line, that was okay, how many cycles did the beam have or pulse have? And what was the wavelength of each of those cycles? Those two factors multiply by one another, give you the spatial pulse length, but then you have divided that by 2. But that number is okay, or the numerical number is okay for your exit resolution remains the same. Clear? For your lateral resolution goals, the numerical value of your the numerical value is going to change. Why? Because, okay, the numerical value of your lateral resolution was the width of the beam, which changes. It decreases in the near zone, then it gets to the lowest at the focus, and then it just, okay, increases in the far zone. Did that make sense? So the main thing, guys, that you have to, is okay, compare here with is that we can see is okay, this and this, this and this, this and this. Let's say it's okay, this and this. Okay. This distance here, which is, you can say it's okay, the distance between the, sorry, two structures. And what is that these two structures are side by side, or perpendicular to the beam's main axis. What is your beam's main axis? We can just, okay, say, okay, we label this like this. And main because, okay, you can say it's okay. This measurement here, this measurement here, this measurement here, this measurement here. Or this line here, yes, okay, makes a line that is transverse to the beam's main axis. That's why this is also called the transverse resolution. Or we say, okay, this is the distance, this is the distance, this is the distance, this is the distance. Now we can just check, yes, okay. A beam. And say, well, okay, if this is okay is your beam. Okay, we can then say it's okay then. This here is okay as the width of the beam at different points. That this width of the beam actually is going to be, yes, okay, the lateral resolution. The remaining is okay. Based on this, can say it's okay. At this point here, it's okay. We will have a bad lateral resolution. At this point here, it's okay. We will have a good lateral resolution. At this point here, it's okay. We will have a bad lateral resolution. And at this point here, it's okay. We will have a bad lateral resolution. Why? Because the width of the beam, which was the numerical value of the lateral resolution at this point here, it's okay, this width. So we can say it's okay if this width of the beam is greater than the distance between the two structures, which we have, and let's say it's okay. This point here, this point here, and this point here. These were all going to give us, okay, as a bad lateral resolution. Whereas, okay, it was the opposite. As we had here, where we still could say that, okay, yes, at the width of this beam OMG. That the width of the beam is okay, we're going to it's okay, be lesser than the distance between your two structures. That was going to give you as okay a good lateral resolution. Yeah, where we could for instance say it's okay here, for instance, if this distance is okay was 3 millimeters, and we could say okay, this distance between the two structures here is okay was 1.5 millimeter, for instance. Yeah. That was a low distance between the structures, and okay, it's a greater width of the beam. Which means it will mean that okay, you had a bad lateral resolution. Whereas at this point here, we could say that okay, as the width of the beam, for instance, okay, is 2 millimeters. And I just say that okay, as the distance between the two structures here as well was going to be as okay, 2 millimeters as well. That will still give you as okay, good lateral resolution. So I equal or less than the distance between the two structures will give as okay. For your numerical value will give you a good lateral resolution. Whereas for your axial resolution goals, it's going to be, you can say, okay, the distance between this structure and this structure. Is it this structure and this structure? This structure and destruction. These distances here. Or what is that these distances are going to be compared to? That's going to be okay. The numerical value of the axial resolution, which was the spatial pulse length divided by 2. This value here is okay, remains constant. There, okay, for your lateral resolution, it's okay, it changes. Here will be greatest. Here we can say, okay, at the focus, for instance, okay, it will be lowest. Any questions? And what were the other names for your lateral resolution? Angular, transverse, and azimuthal. So on page 400, sorry. Page 4, yes, 153. You have a good comparison between axial resolution versus lateral resolution. Did that make sense? Okay. So just take, okay, yes, a short 20 minutes to just, okay, stretch your legs, refill your coffees, hours, and yes, okay, read on your lateral resolution. And when we come back, okay, let's see. Okay, we're going to be talking about, yes, okay, different forms of focusing. And yes, okay, that will be it for this chapter. Clear? So I will see you guys at 10:50. Okay, girls, welcome back. Any questions about your lateral resolution? So everybody clear about lateral resolution? Okay, any questions about what a numerical value would be? Okay. Well. We can then just say that, okay, yes, our next topic is going to be focusing. Clear? Now, what focusing be? We can say, okay, the ability to focus. What is going to happen during focusing? Now, go just keep in mind that, okay, as whenever we say focusing, one thing that we were referring to is the beam, right? Okay, because it was when we were talking about a beam, we said this is where the beam focuses. Or we could say, okay, now, for instance, okay, we will recall as okay, the focal point, or we call that the focus. Right, okay. It was also as okay when we talked about the beam that we call this distance here. Was referred to as okay, the focal depth. The depth at which we focus. And what did it mean to focus? The beam is okay getting to its narrowest point. We also call this distance here as okay, the focal length. Okay, so this could be called either the focal length or the focal distance. What does it mean? The length or the depth at which, okay, yes, the beam focuses. What would it mean to focus? That it actually is okay, gets to its, or that the beam gets to its narrowest depth. What is going to be as okay, we can say, okay, the outcome of a focus. Now, pretty much okay, as clearly as okay, if we talk about focusing in context to as okay, just looking at a thing. The point or the thing that we focus on that is going to become more clear. Clear? Or you will see that more clearly if you look at some things and okay, as you focus on okay, as a specific item in your field of vision. Did that make sense? Right, okay. But since we now know that occurs that focusing, well, okay, what will happen now? We that's okay, where the beam will become the narrowest. That's why we also could say, okay, that this here will also we can okay improve the lateral resolution. Or we could say, okay, at this point here, at the depth at which we focused, that's just okay, where we will have okay, we can say it's okay, the best lateral resolution in yes, okay, the entire course of the beam, whether that was okay as the near zone and okay at the far zone. The point where we will have the best lateral resolution would be yes, okay, at the focus. Why? Because that would mean it's okay where the beam had the lowest numerical value of lateral resolution. What was the numerical value? Mainly is okay when we, the numerical part is that we actually is okay can identify it with a number. And value is just going to use okay how big or small that number is. So that's what you'll call a numerical value. Now, girls, what will be another thing that happens at your focus? or focal point. Yes. What else happens at your focus or focal point?
Is the intensity is the highest of it in the focal point?
Exactly, my dear. Okay, you can say, okay, the greatest intensity. The reason to that is because of, okay, so can you say the lowest area, right? Okay, which may mean, well, okay, diameter measured in either, yes, okay, width or height. Here we say, it's okay, this width, that was going to be as okay, the width of the beam, which means, yes, okay, will lead to, yes, okay, the numerical value of your lateral resolution. But generally, it's okay because in all, yes, okay, dimensions, yes, okay, the beam is at its narrowest at the focal point. It has, okay, as the lowest area. And that lowest area means that, okay, it will have the greatest intensity. Did that make sense? And we can mainly say, okay, that is mainly as okay, what causes that, okay, it's increased concentration of energy in this little area, okay, that you at the focus, yes, okay, your image is going to be, you can say, okay, more clear compared to, okay, the near zone and or far zone. Or what is, okay, as closer to you at the point that you focused at while looking at something, and what's beyond that point. Okay. Did that make sense?
Yeah.
Good. Okay, girls. Now, as far as focusing is concerned, I'm just, well, okay, it's going to become relevant later on. Then whenever, yes, okay, we talk focusing, it's always going to be, okay, focusing off the beam. Clear? Okay, so whenever we talk focusing, it's going to be, yes, okay, focusing off the beam. Because that was going to be the point at which is, okay, the beam gets to its narrowest. Right? So it goes whenever we talk focusing. And yes, okay, that's going to be, yes, okay, repeated again in chapter 12. Again and 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 again. And you will see that, okay, as whenever we talk focusing, it's going to be, okay, how is it that the beam will focus? Okay. Now, we can mainly say, yes, okay, there's going to be two major types of focusing. And because that's okay, there will be two major types of focusing off the beam. So we can say it's okay, beam focusing. Mainly two major types. Okay, one is going to be as okay, what we will call fixed. So when you say fixed focusing or beam focusing, because that's okay, that will be fixed focusing. What we mainly will have in OKS when we say fixed focusing, that will mainly mean that OKS that the beam will only be able to focus at one point. And we can make it okay, just make it further and say it's okay, this one point. If you don't like the word point, you can say it's okay, you can just replace it by depth. If you don't like depth, you can say length. Okay, but this one point depth or length is fixed. Is that clear? Now, what would this mean? That would mainly mean, let's say it's okay, that we, for instance, okay, had a transducer. Now, what we mainly say is, okay, that this transducer here is only going to be able to fix at one point. That point is here. So, okay, yes, it can only fix at one point. But what on top of this is, okay, also make it fixed is that, okay, as this focal point here is going to be fixed. So yes, okay, if it was, let's say it's okay at a depth or a length of, let's say it's okay, 6 centimeters. It's going to remain 6 centimeters. Here, we will not be able to shift it from 6 centimeters to 5 centimeters, or from 6 centimeters to, let's say it's okay, 7 centimeters. It will be fixed. So only able to fix at one point, or focus at one point, or depth, or length, and that is going to remain fixed. That's what we mean by, okay, as fixed focusing.
So question.
Yes, my dear.
So because it's fixed, that means whatever it is constant. It's not going to change.
Pamela?
It's like, so because it's 6 centimeters, it will remain 6 centimeters.
Exactly. Clear? If it was 2 centimeters, it remains 2 centimeters, or 5 centimeters, it remains 5 centimeters, it remains fixed. Did that make sense? Did that make sense?
Yes.
Okay. And what is to notice is that, okay, yes, you're only going to have one single focal depth or focal length or focal point, which is fixed. Okay. So that's okay. When we say fixed focusing, what I mean? Just one focal point or focal depth. And whatever that focal depth or focal point was, that remains fixed. You don't change it. You can't change it. You can't say, well, okay, I know it was 5 centimeters, but I want to increase it to 6 centimeters. I know it was 5 centimeters, but I want to decrease it to 2.5 centimeters. No, if it is 5 centimeters, then 5 centimeters it is. and there's only going to be one focal point, which is fixed. Did that make sense? Clear? Okay, girls. And what you will see, and okay, as we made this, okay, we'll come across this as okay in a later chapter, but it's okay, this kind of focusing here, or fixed focusing, okay, that can also be referred to as, or we may also refer to it as conventional focusing. And or we may even, yes, okay, call this kind of transducer, which only has one fixed focal point, be referred to as a mechanical transducer. Where you then also can say it's okay, then a mechanical transducer can also be referred to as a conventional transducer or a fixed focal point transducer. Clear? Okay, so yes, okay, go ladies in chapter number 12. We will talk of mechanical transducer. And when we end up talking about, yes, okay, how this mechanical transducer, yes, okay, focuses its beam. What we may, yes, okay, we'll say again is that, okay, as this transducer here is going to have a fixed focal point, or has fixed focusing. Which may mean that, okay, yes, it can only focus at one point, or have one focal point, and that focal point is going to be fixed. So that's why we can also say, okay, that this focusing here is okay. It says fixed, or known as conventional focus, is going to be as okay, mechanical focusing. Clear? Okay. So yes, okay, something that is going to, yes, okay. So as you may already see, yes, okay, being brought up again in chapter number 12. Especially, okay, the fixed focusing is okay, especially, okay, when we talk of the mechanical transducer. So one thing that you already is okay, not in the details, but as okay, we'll be able to see about what we call a mechanical transducer is that it only got one focal point. And that one focal point is fixed. If this transducer, for instance, okay, if a mechanical transducer was built to focus at, let's say, okay, a depth of 3 centimeters, then that was going to be as okay, that's focal point or focal depth. And that remains fixed. Now, when we say that it remains fixed, that mainly as okay mean can't be changed. Did you ladies get that?
Yes.
Good. Now, so we can mainly do it this way and say yes, okay. Fixed focus. And we do, okay, yes, because it's also known as conventional focusing. Focus. Or mechanical focus. What did we say about it? Only one focal point. Or if you don't like focal point, you can say it's okay, focus. And as we already have said, that okay, yes, it remains fixed. What did it remain, or what did it mean to remain fixed? Not changeable or adjustable. Did you girls get that? So what I mean is okay in terms of, let's say it's okay an image. Let's say that okay, this here was our image. And we say it's okay that this here, that is your focal point. Or we can actually say that okay, at this distance here, that is okay, that's your focal depth. Because that's okay, if this depth here, for instance, okay, in this case here was 2 centimeters, that would mainly mean that okay, yes, in the entire okay, span of 2 centimeters, that was the only depth at which this beam here was going to be able to focus. Or because this transducer here was going to be able to focus because this will be the point at which it's okay, its beam would be at its narrowest. Although it's okay in this entire bed here. But how it goes as okay from side to side, that's a different discussion. We will take that up in chapter 12. But you can make it as okay, yes, okay, fixed focal point or focal depth mainly or mean that is only going to be able to focus at one single depth, which remains same. Okay. So yes, okay, 2 centimeters, then 2 centimeters, then 2 centimeters, all across the horizon. Yeah. Okay, it will not be able to just okay focus at a shallower depth. So we'll not be able to focus here or at this depth. Or yes, okay, we'll not be able to focus at this depth. Because it was mainly constructed in a way so that the beam would get to its narrowest point at this fixed depth here, which was, let's say it's okay, 2 centimeters. Just as an example. Did that make sense?
Yes.
Now what we can say is as far as okay, yes, your fixed focusing is concerned, there are actually okay 2 ways in which the transducer might have been built to cause this fixed focusing. One may be as okay, what we can call as okay, external. And we can say, okay, just say, okay, external. And okay, it's going to be a fixed focus. But the whole point is as okay in the term external. The other may be as okay, or we can just say as okay and internal. And internal is okay, that the whole point is going to be as okay in internal, but it's still going to be as okay a fixed focus. What does it mean to have a fixed focus? That is going to be as okay, just in both cases here, it's okay. Focus at one, and we can say a single focal depth. Okay. There we say as okay, what if it is going to be as okay and external focusing? How is that going to be managed? Now we just going to just okay, go back to yes, okay, to our basic structure of our transducer. Right, okay. Now we can say as okay that we had yes, okay, the yes, okay, the backing material. We may still have okay as our what we call as okay PCT. Or we also call as okay the active element. But what we actually as okay may have in an external focusing. If the focusing of your beam is due to yes, okay, or it may yes, okay, by the mechanism what we call external focusing. That ahead of the beam, yes, okay, or crystal, sorry. We actually have okay as this thing here. And that's what's going to be as okay a lens. So an external focusing, yes, okay, what do we have? We actually, yes, okay, have a curved lens. So, and we can say it's okay in front of the active element or PCT. Now, what is it that this lens here is going to do? The whole purpose of this lens is, well, let's just do it this way. Oops, sorry. If we say it's okay that this was the transducer, I just say okay, as we have our PCT. And okay, as in front of the PCT is okay, we have the lens. Now, because the sound waves, or we could say, okay, the sound waves made is okay, or have traveled straight. And if they travel straight, oops, probably overdid it. We can say, okay, if it was like this, they were made as okay, just had traveled straight. And what is that you don't have? In this case, it's okay, they didn't reach to a narrowest point, which means to me it's okay, they were not had focused. So it's okay, in a mechanical transducer, where okay, as it is going to be as okay a fixed focusing. But where that fixed focusing is okay, and external fixed focusing is made as okay, achieved by as okay, placing a lens or a curved lens in front of your PCT. And what is it that it actually is okay do to the sound waves as it passes through this lens? Is going to, yes, okay, make them merge. And that will mainly mean that, okay, yes, that they actually, yes, okay, will merge together to reach to, yes, okay, and narrow, the beam will actually, yes, okay, reach to its narrowest point at a fixed depth or at a certain depth. And this is then going to be as okay, you can say it's okay, the focal depth. And yes, okay, girls, you'll still have okay as you were, you can say it's okay, you're matching there. Did you girls get that? So if in a mechanical transducer, where we may is okay, just have one fixed focal point, and that focus is made as okay, achieved by placing a curved lens in front of your PCT, where it's actually going to be okay, this curved lens here that's going to okay cause the beams, sound waves to refract and cause them to yes okay narrow down to yes okay its narrowest at a certain depth, which we call as focusing. But that kind of focusing where we use okay as a curved lens in front of the PCT, that the kind of fixed focusing is going to be as okay what we call external focusing. Because as I said, had it not been for this curved lens here, well, okay, yes, the sound waves would mean as okay, just had traveled straight. But the mechanism that we actually just okay might have used to just okay change the course and call it okay these waves yes okay actually is okay to refract to a greater or lesser extent is going to just okay by help of a lens. Okay. Did that make sense? So we
I have
can
a
make it
question.
just a second, my dear. So we can make that okay, the degree to which is okay, the waves refract and reaches to yes, okay, that fixed focal point is going to be determined by us, okay, how great the curve of the lens is. Now you can make it okay, the greater the curve of lens, means okay, will lead to yes, okay, a greater refraction of the sound waves. Yes, Shaq.
Hold on. I'm sorry, I'm just writing this down. I think you answered it. So because of the curve, I think I'm getting confused. So the curve, because of the curve, it basically has a different angle for when it refracts.
Exactly.
Okay.
And why do we call it a lens? Because it does the same to the sound waves. as the lens of your eyes due to light rays. What does the lens of your eyes do? Not contact lenses, your actual lens. It refracts the light so that it's able to focus. Now, some people, yes, okay, may need, yes, okay, some extra help to focus in form of glasses. Clear? But what is it to have? What is it that you have in glasses? Yes, okay, that piece of glass that they put in the glasses is called a lens. Did that make sense? Okay.
Yes.
Oh, yes, okay. Even if you take, yes, okay, the lens of a camera. Now, why do they call it a lens? Mainly because, yes, okay, that is going to be the tool or the piece or, yes, okay, the object that you have in the camera that actually is, okay, enables you to focus. On the thing that you want to, yes, okay, take a picture of. Did that make sense? So here we can mainly say, okay, that, okay, as an external focusing, what is it that you have? We actually, as okay, have an additional piece in the transducer, which is going to be a lens. And what is that lens is going to do? That is actually, as okay, now going to be curved. It's going to be a curved lens in front of the PCT, which actually is okay, will refract the beam. Or we can say it's okay, refract your pulse waves. And what happens when they refract? They're most likely, okay, it's like, okay, merging together. Did that make sense? And eventually, it's okay, as they keep on merging, all depend upon the degree upon, it's okay, at which they merge. At some point, it's okay, that beam will get to its narrowest point. And that distance from your transducer, which it reaches to its narrowest point, is going to be its focal depth. But that is going to be fixed because it's all determined upon how, yes, okay, your transducer was built. What was the curve of that lens in your transducer? So you can say as, okay, greater curve, greater refraction. The greater the refraction, well, okay, the shallower the focal depth. Okay. But when we had a curved lens in front of the PCT, that curved lens was going to, as okay, refract the beams, oh sorry, the waves, for them to, as okay, focus at a certain point, which may mean that, okay, as they reach to this narrowest diameter at a certain depth, that kind of fixed focusing, because that was going to be fixed, was what we call as, okay, an external focusing. Is that clear? Is that clear, ladies?
Yes.
Good.
Yes.
Okay. Likewise, or similarly, just a slight difference. is, well, okay, as we still had another form of, okay, as fixed focusing, which we also could call as, okay, conventional focusing or mechanical focusing, which we call as, okay, an internal focusing, or we can say an internal fixed focusing, because it's still going to be as, okay, at one fixed focal point. But why do we call it internal? Do you ladies mind if I go to another slide?
I'll go.
Good, thank you, Deb. So we can mainly say, okay, if this here is, okay, it was a transducer, maybe mainly says, okay, because it's okay, for instance, okay, this here is, okay, was the backing material. Okay, we can say it's okay, this here is, okay, I guess the matching layer. We can say it's okay, we had the let's say it's okay, active element crystal or PCT. But it's okay, in front of this PCT here is okay, if you find this, okay, you had this. Lens. This whole setup here is okay, was going to be as okay, a fixed focusing, but primary as okay, due to as okay, the lens. We'll call it as okay, an external focus. The other one is going to be as okay, what we call an internal focus. Okay, where we still can say as okay, well, we still have okay as our backing material. Yeah, we will still have as okay, our matching layer. Yes, of course, we will also yes, okay, have our active element or PCT. But when we say as okay, internal focus, which is going to be as okay, fixed. What we actually have in this kind of setting here is that okay, as it is going to be as okay, the surface of the PCT itself. Curved surface of the PCT, or what we call active element. And that is actually that's okay, going to cause that, okay, yes, as the sound waves hits this, that they actually is okay, will start just okay, we can say it's okay, emerging. And okay, reach to a fixed focal point. So the difference, the main difference between yes, okay, and internal focusing versus external focusing is that in internal focusing is the surface of the PCT itself that is going to be curved. Okay. Whereas if you said external focusing, that's okay, it's going to just okay be that in front of your PCT is going to be as okay. A curved lens that is going to just okay cause the beam to focus at a point. But in both cases, whether it was curved surface of the PCT or yes, okay, you can say a curved lens in front of the PCT. In both instances, okay, the focal point or focal depth would be fixed. What would determine that focal point? It was all determined upon, that's okay, how great the curve of your lens was, or how great the curve of your PCT surface had. Did that make any sense at all?
Yes.
So this kind of focusing here is what you call a fixed focusing. So you can't change it. It is what it is. It's as the PC, it's as okay, your transducer is built. What kind of lens they put into it? Well, what kind? Me is okay, just how big or small of a curve does it has? Or it's okay, how big or small it's okay, or how much was the curve on the surface of the PCT. But the difference is, if you use it as a lens, that will be external focusing. If you use the surface of the PCT being curved itself, that's going to be as okay, what we'll refer to as internal focusing. But in both cases, okay, these were fixed. Where do we see fixed? We also call it, okay, mechanical focusing. So that's what we will see in what we will call a mechanical transducer. And the main point is, well, okay, it only got one focal point, a focal depth. I'm designed to just focus at a depth of 3 centimeters. Clear? I can't focus at 5 centimeters. I can't focus at 1 centimeter. So my focal depth was fixed. Did that make sense? Now, girls, please. There's a difference between depth of image and focusing. Okay. Okay. I may be able to see up to, yes, okay, a distance of 10 miles. But it's only going to be, let's say, yes, okay, 5 miles that I'll be able to focus. Which may mean that, okay, what happens at a distance of 5 miles, that's what I'm going to be able to see the clearest. I can still see for the first 4 miles, 4.99 miles. I still be able to say, okay, see for the next 5 miles, which may go as a total depth of vision or field of vision. That's okay, 10 miles. But the depth or the distance at which I'm able to focus is fixed, which is 5 miles. Okay, so that's okay. A lot of students, that's okay, end up confusing these two things here. So that's okay. You increasing the depth of the image is not going to affect your focal depth. Did that make sense?
I have a question. So they're not related?
No.
Okay.
If I say, well, okay, yes, my focal depth is 5 miles is probably too much. That's okay, 5 meters. My focal depth is 5 meters. Which may mean it's okay, wherever I walk, what happens at a distance of 5 meters in front of me, that's what I'm going to be able to see the clearest. But even yes, okay, if I go from a point where I'm able to see 10 meters ahead to 20 meters ahead or 30 meters ahead of me, by my focal depth is our focal distance is 5 centimeters or 5 meters. That's what it's going to remain. So they are not related, no. Or just look at it in this way. Now, what did we just say as okay that your depth of image was? Right? You can here say it's okay that our depth of image was 1, 2, 3, 4. 4 centimeters. Let's say that okay, as the transducer that we use here has okay as a focal depth, which is going to say okay, in this case, okay, be fixed, and we say it's okay. We say that that is 2 centimeters. What that mean? That this will be the depth at which it is able to focus, right? Did that make sense?
Yes.
We have the same transducer with the same focal, with the same focal depth. What do we do now? We increase the depth of your image. Because this is still 1 centimeter, 2 centimeter, 3 centimeters, 4 centimeters, 5 centimeters, 6 centimeters, 7 centimeters. What did we do here? We increased the depth of image from 4 to 7 centimeters, right? Right? But the transducer was still the same. And okay, as its focal depth was fixed at 2 centimeters. So it will mean, okay, this will be as okay the point of the image where it focuses. Did that make sense? Did that make sense?
Yes.
So here is okay, and we say it's okay, this was fixed. Which means it's okay when we say it's okay, it's fixed, I mean it's okay, meant that okay, it can't be changed. Why? Because in either case, whether it's okay, it was at a reviewed at a shallower depth or reviewed at a greater depth, that the beam was going to as okay focus at a fixed depth. Which was your focal depth or focal length. Whereas these numbers out here or here, that was okay depth of image. depth of image. You just say as okay, this is me, as okay. Walking out, yes, okay, on a day where okay, there's a dense fog. What happens? There's a low visibility. I may only be able to see up to 5 feet or 4 feet. Because okay, after 4 feet, yes, okay, because it's okay, there's no visibility. This is me walking outside as okay on a nice sunny day. No clouds, no fog, no nothing. Well, okay, no nothing. So it's okay, there's a great visibility. I may be able to see up just okay 70 feet. Or that's okay, 7 feet or something like that. But it's okay. I'll still only be able to focus at a depth of 2 centimeters or 2 feet. Why? Because it's okay, my focal depth was fixed. Did that make sense? Have any of you ever tried to just okay play with a magnifying glass? Okay. Now, my idea, besides just okay, make things look bigger. What else is it that you can do with a magnifying glass?
If you turn it around, it can make it a little smaller. Like it makes it further away. Like at least mine did. If it was like big on one side, and then if you turned it the other way, it made it farther away.
Okay, but you can, okay, but what actually is it that you see?
Like all the details. It has a lens.
Yeah, the lens, the little round thing.
Okay. Okay, I said we're magnified. That's mean yes, okay. But have any of you ever tried to just okay hold a magnifying glass? Well, okay, not looking at the sun, but it's okay against the sun.
No, but I saw to do it in like the movies.
No, don't do it like this.
Or-
The other way around. But you can actually just okay use a magnifying glass to turn on a fire.
yeah.
And how do you do that? That's mainly because okay, you can say it's okay, the light energy actually is okay will be focused onto it's okay a piece of paper, and you can say it's okay, the narrower you make that focal point of focusing of the beam of light on the paper, it will turn a fire on its fire. And what one of my students once said, not in your group, that you can actually it's okay make earthworms explode as well. So she tried to do that, and okay, yes, okay, the earthworm will actually it's okay explode. Now, girls, please don't do that, because okay, that's terrorism against a harmless object or substance or thing called an earthworm. Okay, but that was your focusing. Okay. Okay, girls. Now just take a short, okay, not short, take your lunch break, and when we come back, we will talk about it's okay, what we call electronic focusing. Or we will also, it's okay, just talk a bit about it, okay, what it means to be, yes, okay, and array focusing. So CU goes at 1 o'clock. Okay.
Okay.
So that is just because we can mainly say, okay, now we said we had focusing, and we can mainly say, okay, see there is going to be two major types. One was fixed, and since it is fixed, it's going to be as okay, mechanical. Clear? And in the fixed or mechanical, we had ideas, okay, what we call internal and or external. Yep. Then, ladies, and we can maybe say, okay, the actual details of this is going to, it's okay, what we will talk about in chapter 12. But we actually have, okay, as a kind of focusing, which is going to be, it's okay, what we can call electronic focusing. And if you look at the word electronic, that mainly means that, okay, as in this case, yes, okay, the focusing is going to be, we can say, okay, controlled by the electronics of the ultrasound system. Clear? So it's not just going to be, yes, okay, we can say it's not only going to be, yes, okay, the size and shape of the PCT that will determine the focusing, but it's rather going to be, as okay, the electronics of the system. Now, the thing about okay, electronic focusing is, because it's okay that it can be changed. Which mainly will mean that, okay, it's just because a transducer is made in the way that it is made, doesn't mean that, okay, yes, it only will be focused at one point. So we can say, it's okay, we can actually, it's okay, change the focal depth or focal point. Okay, from 1 centimeter to any other depth. Is that clear?
Yes.
Okay, so in that way, it's okay, we can mean it's okay that this is going to be non-fixed, or we say not fixed focusing. Then we actually can change it. Another term that, yes, okay, we will come across is going to, yes, okay, which is still going to be, yes, okay, only found in the electronic focusing, is going to be, yes, okay, array. Okay, so if you say, yes, okay, array focusing, that will mainly mean that, okay, yes, is going to be multiple focal points. Did that make sense? Okay, now let us just, okay, let's compare this to it's okay, a fixed and okay, as mechanical focusing, because when we say fixed and or mechanical focusing, let's say that, okay, yes, our focal depth was 2 centimeters. Difference, yes, okay, in this instance for this transducer, yes, okay, was because it had, okay, as a fixed focal depth of 2 centimeters. Okay, but we may say, okay, now first of all, we only had one focal depth. Which was at 2 centimeters. The second thing we said, okay, this single focal point here, so okay, was fixed, which mainly means that, okay, as we were not going to make it focus at 1 centimeter or 1.5. We were not going to be able to just, okay, focus at anything that's, okay, greater than 2 centimeters. Let's say it's, okay, 3, 4, 5, 6, whatever. Did that make sense? Because this focal point here is, okay, was fixed. So that's why we made as, okay, call this one here as, okay, fixed focus or fixed focusing, which we made as, okay, we'll see in what we call as, okay, a mechanical transducer. Now girls, when we say as, okay, or mainly because, okay, its focusing is going to be mechanical. Okay, what about the two types of mechanisms? Either yes, okay, external focusing or external focusing. Clear? Whereas, okay, we say electronic focusing. Right, okay. If we say, for instance, okay, electronic focusing. Now there's going to be 2 points of, okay, as electronic focusing. First of all, yes, okay, it's going to, yes, okay, be controlled by the electronics of your system. That's okay, the actual details of that is okay, we'll talk more about that in chapter number 12. But here it's not going to be as okay, not really as okay, the configuration or the construction or the makeup of the transducer that will determine the focal point by as okay, mainly as okay, that along with the way that the electronics of our ultrasound system works. Okay, but who determines how we want the system to work? That would be us. We just pass a command and okay, yes, the system will work accordingly and do yes, okay, what it wants us or what we want it to do. And what is that we want it to do? Oh, yes, okay, can make it do. We can say, well, okay, we actually, it's okay, would like you to be able to, let's say, it's okay, change the focal depth. So when we turn on the system, it may say, well, okay, yes, right now, yes, okay, I just have a focal depth of, let's say, it's okay, 3 centimeters. But what we made as okay can do is say, well, okay, we don't want you to focus at 3 centimeters. We want you to focus at, let's say, as okay, 4 centimeters, or 5 centimeters, or 6 centimeters or so. Or even go to a shallower depth, let's say, as okay, 2 centimeters, 1 centimeter depth. Okay, so we can actually, as okay, with help of okay, as a little twist and turning, change the focus depth of our transducer. So mainly is okay because we are able to change it. That's how it does not, it's not fixed. Is that clear? Is that clear, girls?
Yes.
Okay. On your system, yes, okay, this focal depth or focal, or change of focal depth, we can actually say that that's going to, yes, okay, by changing what we can call as, okay, the focus position. Or you may see as, okay, a short abbreviation of this on your, for some of your function keys. Okay, which is going to be as, okay, focus or foc plus. That, okay, yes, when you actually, it's okay, turn that anti-clockwise, you will just, okay, move to a shallower depth, or clockwise, go to a greater depth. Did that make sense? So it was not fixed. You could actually, yes, okay, move it up, move it down.
I have a question.
Yes, check.
What does that say in purple?
Focus plus. Just, okay, as an abbreviation for, as, okay, focal position. But no matter what, if it started as, okay, being focused at this point, I mean, it's okay because it's okay, the system main is, okay, just run so that the beam is at its narrowest at this depth. Let's say it's okay, you change the focal position to a greater depth. Let's say it's okay to a depth of 4 centimeters rather than 3 centimeters. That may mean that now it's okay, the beam is okay, focus at this depth. Did that make sense? You want to focus at a shallower depth. Let's say it's okay, 2 centimeters. Well, okay, yes, you do that. And okay, what will happen then? Your beam is okay, or me is okay, just focus at this depth here. Did that make sense?
I have another question.
Just a sec, my dear. Right? Did that make any sense? So what you actually can do is just, okay, you can change your focal position. Clear? And why mainly as, okay, because in this system here is, okay, what we mainly will have is not going to be as, okay, a fixed focusing. But rather is, okay, because all focus is now going to be more as, okay, electronically controlled. Any questions?
Yes,
Okay, yeah.
and we, I'm sorry, so we changed the focal depth by adjusting it by the image depth, right? Like that
No,
knob.
no. I just said that before going on break. Those are two completely
Oh, yeah,
different
it's
things.
not the same. Yeah, you're right. I'm sorry.
But just keep in mind, yes, okay, if you want to focus at a depth of 6 centimeters, you have to have your image to at least 6 centimeters depth. But you can still have, okay, as your image at 6 centimeters, but still be focused at, let's say, 3 centimeters, 4 centimeters, 2 centimeters, 5 centimeters. So those are two completely different things. Okay, girls? Now, those of you who, yes, okay, took a selfie with, yes, okay, with the system the other day. Yes, okay, we mean, yes, okay, Sarah, yes, okay, we had these 5 small knobs here. Where I said, okay, this knob, this far right knob here was, okay, yes, your power output. Then you mainly will see that, okay, yes, and especially as, okay, when the system is on in B mode, that this knob here Right next to it is okay. On top of it is okay. On the window is going to be two things. One is going to be as okay, what says, we can say it's okay, focus, pause. And then, okay, as another function is going to be as okay, what will be as okay. Focus, num, N-U-M. Okay. Now, what that mainly will mean that, okay, as this knob here actually is okay, got, in this case, it's okay, got two functions. One is that we actually is okay, can change the focal position. Or we can say, okay, we can change the position of the focal point. Move it to a shallower depth, move it to a greater depth. That is going to be done by us, okay, adjusting focus position. Clear? Okay. Now that's going to only be, yes, okay, you actually, that's okay, by twisting this knob, the focus position is going to happen, or okay, change of the focal point, or change of your focus position is going to happen is just, okay, focus pause is outside the bracket. Because this time, yes, okay, what you will see is that focus num is going to be as okay inside the bracket. So we can say, okay, the function that's going to be as okay inside the bracket is going to be as okay, what will be the inactive function at this point. Clear? Did that make sense? So yes, okay, you will come across as okay in different modes that some knobs or buttons may actually have as okay two functions associated to it. Okay, where one function is going to be as okay outside the bracket, and then you have okay as a function that is inside the bracket, written on the screen right next to it. Now, for you to know which function is active, is going to be as okay the function that is going to be outside the bracket. That will be active. So if it's, for instance, okay, it's focus plus, that is active. That will mainly mean that, okay, so when you move this or twist on this knob here, you actually, as okay, will be able to, as okay, move your focal point or focal positions. Did that make sense? Where moving of the position is by as okay, moving to a shallower depth or deeper depth. Did you girls get that?
Yeah.
Good. Anybody who is in doubt?
I am.
Okay.
Maybe I just need clarification. So the screen, it tells you what's, like, I'm going to be confused. Like, so the screen tells you what is active.
Listen. And that's why I say yes, okay, this thing should not be taught online. But anyways, my opinion means shit. If you remember on your keyboard, we had these small 5 keys here. Okay, your depth, the one by which you control the depth, is over here. Okay, so I talked about the depth the other day where you actually is okay, could turn it clockwise and okay, as that would increase the depth. Okay, where we went from 8 centimeters all the way down to yes, okay, 20 centimeters. Clear? But then, yes, okay, on your keyboard, we had these 5 knobs here. Okay, now these knobs here is okay. Right next to it, that's okay, was the screen. That's okay, this screen, yes, okay, touch screen. So that's going to be, yes, okay, some other functions and things like that on the screen as well. But right next to, yes, okay, each knob, you actually will see different things written. Now that's first of all going to depend upon, yes, okay, what mode is on. Now in your B mode, yes, okay, this one here, that was going to be, yes, okay, your power output. Then we went all low and all right now, yes, okay, we are talking about, yes, okay, this knob here. So yes, okay, in B mode, this is going to, yes, okay, have 2 functions associated to it. One is going to be, as okay, we can say it's okay, the position or focus position. The other one is going to be what we can call as okay, focal number. Okay. Now, what you may see as okay, whenever this system is on or function is on, well, it's going to be on anyways, but you would then say, okay, now if I twist and turn it on this function here, or this knob here, since it has 2 functions associated to it, I only want to make change in one of them and not the other. How would you know? Now, if okay, you want just okay, for instance, change your focus position, that will mainly mean that okay, as this focus number here is going to be as okay inside the bracket. So you actually see one function as okay written outside the bracket, one written inside the bracket. Where? Right next to yes, okay, to the screen. Right next to this button. Did that make sense?
Yeah.
Good. Now come, so that's okay. If you say focal pause, it's not going to be written the whole number focals position. It's not going to be as okay, FOC for focus, PUS for position. But if that is outside the bracket and you twist and turn with this knob here, you actually is okay, can move your focal point up to a shallower depth, or you can move the focal point down to a deeper depth. Did that make sense?
Yes.
Okay. But deeper depth, my dear, is still going to, well, okay, you still have to make sure that, okay, yes, your image is going on to that depth that you want to, yes, okay, bring the focus down to. You can't say, well, I want to focus at a depth of, let's say, 10 centimeters. And the imaging depth is only, let's say, it's okay, 6 centimeters. That's not going to be possible. Because these 10 centimeters here is beyond the depth of your images.
Mhm.
Did that make sense?
Yeah.
Okay. But the way by which you can either is okay, increase your focal depth or decrease your focal depth. Okay, by me, that's okay, turning this clock, that's okay, knob here clockwise or counterclockwise. Where I just say as okay, clockwise is increasing. So increasing focal position or increasing focal depth. That you go from a shallower depth to a deeper depth. Or decreasing will be turning it as one against the clock or counterclockwise, which means okay, it means that you will bring your focal position to a shallower depth. Did that make sense?
Yes.
Good. Now goes this knob here has another function. And that's what I say is okay, was the other point of okay, yes, your electronic focusing, which we actually as okay, will call as okay, array focusing. Or mainly as okay, any transducer we have, this capacity is going to be called an array transducer. So what is that the word array actually would mean here is that not just one focal point, but we actually are able to have multiple focal points. So you may not be just stuck at, says, okay, just focusing at one depth, but you can actually, okay, have a focus at multiple depths at the same time. Did that make sense? And that is what we will call array. So you come across this term here, it's okay, again and again and again and again in chapter number 12. But that's okay when we say this. Array focusing. First of all, there's going to be no doubt about it. It is going to be as okay electronic focusing. Except from one transducer. But in 9th, that's okay. Whenever you say it's okay electronic focusing, it is always going to be okay array focusing, which mainly or mean we can say okay that we have the ability to focus at multiple depths. Yeah, not just focused at okay as one point or one single depth, whichever it is. Okay, so you may have an image, and we say it's okay. Let's say that these here is okay are the pointers that indicate our depth of the image. So this is going to be, because it's okay, 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeter, 4 centimeter, 5 centimeter, 6 centimeters. Clear? Let us just assume that okay, yes, in this case, yes, okay, we have still only yes, okay, focused at one depth, which was 3 centimeters. You say, well, okay, I want to, yes, okay, not only yes, okay, be focused at 3 centimeters. I also want to, yes, okay, focus at more than one point at this time. So you can actually, yes, okay, focus at 2 centimeters. You can also focus at 4 centimeters. You can say, well, let me focus at 5 centimeters. So what is it that you have now? You don't only have one focal point, but you actually have multiple focal points. Even if it was just 2 focal points, it's going to be considered more than one. So anything more than one is going to be considered multiple. Clear? And what do we call this kind of focusing? That means okay, what we will call array focusing. How are we going to be able to, yes, okay, do that? It will be, yes, okay, the electronics of the system that enable you to focus at multiple points. Now, how do you pass or yes, okay, convey the message to the system? I want you to focus at multiple points, not just one point. I want you to focus at more than one depth at a time. Try to verbally say that to the machine. It doesn't understand a word that you're saying because it doesn't have ears. Okay. Did that make sense? So there gotta be as okay some means or some mechanism or some way by which we are able to just okay convey that message to our system. Clear? And dear girl, that's the same knob here. Because what is the other function that it says? Focal numbers. Which means as okay, will just mean as okay, because it's okay, the number of focal points. Did that make sense? Right? Okay, so focal num means nothing but mainly as okay, just the number of focal points. Now, if you have yes, okay, you can say it's okay. If your display is okay, show this kind of configuration right next to this knob here. Your question is, but yes, okay, if I twist and turn this knob here, it's okay, what's going to happen? It's just going to be, it's okay, the focal position moving up and down. Right, okay. Because that's the function that is outside the bracket, that is the active one. So the question comes, how do you, okay, make these two hairs, okay, switch position? That's contagious, dear. Okay, girls, it doesn't need a lot of biceps. Okay, just a slight touch on the button. You may just, okay, just push it a little bit. And the next thing you will see, you told the system, well, okay, yes, move focal position into the bracket and focus number out of the bracket. And what do you have now? Now focus number is going to be outside the bracket, right? And now when you twist and turn this knob here, okay, so it's made as okay, just made as okay, just by slightly as okay. Pushing on this button here is going to just okay. Focal number or focal num comes outside the bracket. And okay, as focal position gets inside the bracket. And now, yes, okay, when you twist and turn on this knob here, it may, yes, okay, increase the number of focal points from 1 to 2, 2 to 3, 3 to 4, 4 to 5. Did you get that? And that's when we, yes, okay, turn it clockwise, because that means, yes, okay, mean increase. Or, yes, okay, if you turn it anti-clockwise, it will decrease the number of focal points. So that's why, yes, okay, you actually, yes, okay, will be able to say, yes, okay, well, not only focus at 3 centimeters, also focus at 2 centimeters, even go, yes, okay, further focus at 4 centimeters. Now goes, let's just say, yes, okay, that now these, yes, okay, 3 points or 3 depths here, 2 centimeters, 3 centimeters, 4 centimeters. These were our focal points. How would you know that you actually, as okay, are focusing on these 3 depths here? Now, what you actually, as okay, may see right next to, yes, okay, each of these numbers here. Now, some system, yes, okay, may show you, yes, okay, something that looks like a little triangle or arrowhead right next to it. So what would that indicate? That may actually indicate that, okay, these are your focal points or focal depths. Is that clear? So now you would know that, okay, that's mainly because you see, yes, okay, these small triangles here, right next to the depth of 2 centimeters, 3 centimeters, 4 centimeters, that these are my focal points. And yes, okay, girls, if you want, yes, okay, move these 3 focal points, yes, okay, to a greater depth, what do? Just push on the button. And okay, there will be a switch, and then you can make this, okay, just turn it clockwise, and okay, remove it down from 2, 3, 4 to 3, 4, 5. 3, 4, 5 to 4, 5, 6. As you twist this button. Because okay, now your main is okay, just changing is okay, the position. Or if you want to move them up, well, okay. Good. Just turn it anti-clockwise. So what we actually is okay are doing by main is okay, just pushing on a button and or twisting it clockwise, anti-clockwise. We actually is okay convey a message to the electronics of the system. Change your behavior a little bit because we want you to focus at this depth. We want you to focus at this depth. We want you to focus at this depth. Or sometime we may even put some extra burden on the shoulders of the system and say, well, okay, we want you to focus at these multiple depths. Not just one depth, but multiple depths. Okay. Now the basic electronics and all about all this here is something that we'll talk more about in detail. But when we get to that, chapter number 12. Okay, but that's mainly so mainly because it is controlled by the electronics of the system that we call it electronic focusing. Okay, which in most instances is going to be what we call array focusing. Because as a result of that, we are actually able to not just focus at one depth, which was fixed, but we can move that focal point up and down. We can even increase the number of focal points from 1 to 2, 2 to 3, 3 to 4, 5 to 6. Okay. Now there are some plus points of that, and there are some negative points. What could be the plus point of OKS increasing the number of your focal depths? Anybody?
Better lateral resolution.
I mean,
It's better improve lateral resolution
at
at depth
okay, what depth?
of image of the beam.
Okay, at multiple depths.
Yes, the beam make you
Right,
make
okay.
narrower beam. yeah.
Exactly. So you got you can say you got an improved lateral resolution at multiple depths because you focus at multiple depths, right? What happens when you focus? The beam gets narrower, right? What happens when the beam gets narrower? You'll probably we'll get a better lateral resolution, at that depth. Where was the answer to this crazy question here hidden? Where was the answer to this crazy question here hidden? Because some of you may, might have been scratching your heads and saying, Mike never told us that. Oh, yes, I did. Indirectly. Because if you know that, the narrower the beam, the better the lateral resolution. And where do we have a narrowest beam? At the focus. So if you tell the beam to focus at multiple depths, you actually indirectly also tell it, give me a better lateral resolution at these depths here, right? Did that make sense? So if you start thinking like that, that's when physics becomes, or can become, as quite more easier. Yes, ladies. Any questions? Any questions, girls? Now you're on page 156, sorry. May see, yes, okay, 4 points of, yes, okay, what happens to the beam when it focuses. Okay, now what does the first one read out to? The beam diameter in the near field. Now, what is another name for near field?
Near zone.
Near zone. Okay, what's another name for near zone then? Besides near field.
I don't think I'm gonna say it right, but I think it's like. It
Want me
starts
to-
with an F.
Okay, F.
Fraunhofer zone?
Fresnel zone?
Yes,
Fresnel
Fresnel zone.
Fresnel. Fraunhofer idea, that's your far zone. Clear? Or far field. Okay. Okay. And focal zone narrows. Okay, as we can mainly says, okay, that's mainly okay, what happens to your near zone, right? That it becomes narrower and narrower and narrower, and that's how it's okay, your beam focuses. Clear? The focus is moved towards, in other words, that's okay, the near zone is reduced. Well, okay, just something that you have to, that's okay, remember. Okay. So that's okay, when you focus, actually, what actually may happen is that, okay, the focal zone moves closer to your transducer. Now here's okay the third point, and that's actually that's okay going to be more actually that's okay in chapter 12. But anyways, what the mainly says okay as the beam focuses, you can mainly says okay that due to as okay point number one, that the diameter as okay decreases in the near zone and far or near field and focal zone. That will improve your lateral resolution in those areas. But what happens to your beam in the far zone is that actually is okay, diverges out. Okay. Now what we have said so far was that okay, as if the beam goes like this, it's going to yes, okay, diverge out like that. But what actually happens is the beam may narrow like this, and in the far zone goes more out like that. So that's why it's okay, your lateral resolution is always going to be as okay, very degraded in the far zone. Clear? Did that make sense? Okay, now the 4-1 says, okay, the size of the focal zone is reduced. Okay, and okay, that's mainly as okay as a result of point number 3. Why? Because, okay, half of your focal zone was in the near zone, half of your focal zone was in the far zone. But it's okay, actually, it's okay, it gets reduced because of the sudden widening of the beam in the far zone. Okay. Now, ladies. And okay, then we talk about, okay, yeah, we can take those tomorrow. To those tomorrow. Oh. Okay, goes. Any last words? Any last words? Now, girls, just try to, yes, okay, look at, okay, yes, the 12 questions on page 157, 158. You will have to, yes, okay, mean, yes, okay, for some of them, I guess, okay, as refers to figure 10, 11. Okay. But we will take these questions and, okay, as the questions in the back of the book up tomorrow. And try to, yes, okay, go over them together. And, okay, yes, look at, okay, what kind of questions we can get from lateral resolution and axial resolution. Okay. So what were the names for your lateral resolution? Or synonyms or nicknames are also known as, or as.
Transverse.
Transverse, good, okay.
Angular.
Angular. And,
I can't pronounce the other one.
okay, then no ice cream for you on next.
I like ice cream.
Okay.
I can't say it. I'm sorry.
You can't say it, you started, so either you say it or you don't say it, or you fail saying it. So Dr. King, try to say it.
Azimuthal.
Okay. You like ice cream, right?
Yes.
Okay. How much?
A lot.
A lot.
Is it chocolate ice cream?
Okay. Now after this, you're going to hate ice cream because you're going to buy ice cream for all of the other girls.
I don't mind.
You don't mind?
No.
So next time we meet up, Dr. King is going to, yes, okay, treat us with an ice cream. It's azimuthal, right? Okay.
Azimuthal.
Azimuthal. They're crazy. Like, okay, why couldn't they just have made something with E?
Right.
Expressive or whatever. And okay, as the mnemonic for, yes, okay, lateral resolution while being late. Okay. So yes, okay, it's lateral, it's angular, it's transverse, and yes, okay, the azimuthal. Clear? What were the other names for your longitudinal resolution? What were the other names for your longitudinal resolution?
Oh, longitudinal, axle. Longitudinal, axle, radical, range, and depth.
Radical?
Right?
Or is it
Right.
radial?
Radial.
Yeah, okay.
Sorry,
Depth,
it's
okay, yeah,
radial.
okay, yeah. That's fine. Okay, so that's okay. It would be axial, longitudinal, range, radial, and depth resolution. Clear? What's the numerical value for range resolution? What's the numerical value for range resolution?
Is it the pulse of the? I think I'm saying, is the pulse of the sound beam? No?
What was the question again?
What's the numerical value of
What's
the?
the numerical value of your range resolution?
Isn't it the,
Or is it a spatial pulse? Like,
yes, spatial pulse length, I believe, divided by 2.
Exactly.
oh,
Don't
the-
get confused by range resolution because that was just another name for your axial resolution, right?
Yeah.
Clear? So if you know that and you know it's okay what the numerical value for your axial resolution is, that's the same. Yeah, so half of your spatial pulse length. Clear? In what unit do we, yes, okay, measure the lateral resolution?
centimeters?
Okay, and what if I say millimeters? It doesn't really matter. As long as it is a unit of distance or length, it should be fine.
Okay,
Yeah,
yes.
okay. So yes, okay, centimeters, millimeters, micrometers, decimeter, kilometers. Probably not, but like, as long as it is a unit of distance, yes, okay, that should be fine. Now, ladies, if the width of your beam is greater than the distance of two structures lying front to back of one another, would you have a good lateral resolution? A bad lateral resolution? Or not determinable lateral resolution?
Can you repeat the question for me? I heard you, but it's just, I'm trying
You
to,
heard me.
yes,
Okay. Okay. If the distance between two structures
Mhm.
lying front to back of one another is greater than the width of the beam, do you get a good lateral resolution, a bad lateral resolution, or it can't be determined?
A poor
a
resolution.
poor one because the distance is too, it's greater than the beam.
Mm.
I would say.
Cannot be determined because it's
Exactly.
about axial resolution when it's
The thing that I said was the explaining is okay, your axial resolution where particle or structure is in front and behind.
Okay,
Clear?
so it's in
So if
front.
we're only had been correct, the answer were only had been correct had it said the side to side location.
Oh,
Or yes, okay, a distance between, yes, okay, two structures located side by side. And you said that, okay, here the beam is wider than that distance, then it will be a poor. But since I says, okay, structures back and forth, or front and behind, That is how, yes, okay, your axial resolution is determined. And that is not determined by the beam. That was your pulse or spatial pulse length. Okay, ladies.
Yes.
So yes, okay, you will come across questions like these in the exercise. So yes, okay, we will do those questions. That's okay tomorrow. Okay, and then see yes, okay, if we have any time left. Why yes, okay, go. This chapter here is important. So see you guys tomorrow with okay, yes, the exercise and exercise exam review questions, and okay, yes, then we go from there. Okay. Have
Okay.
fun. Enjoy.
Thank you. Good night.
Thank
Chill.
you. Bye.
Okay. Bye-bye, girls.
Thank you.
You're welcome, dear.
Sure.
Yeah, just a second. Yeah.